we just looked at how much energy it would take to promote an electron from n equals 1 to n equals 3. When I say promote, I mean make it transition or move from n equals 1 to n equals 3. And we've determined, using the Rydberg constant and our expression for energy at a particular energy level, we were able to calculate the change in energy for that transition to be 1.937 times 10 to the minus 18 joules. And so what we said that most times, or a lot of times, that transition will be made to happen because an atom will absorb a photon that has some energy. And it will have the energy that exactly corresponds to the energy of that transition. So this change in energy will be equal to the energy of the photon that's absorbed. So if we know the energy of the photon, we can then use our expressions that relate wavelength or frequency to energy to determine what the wavelength or frequency of that photon might be. Now, we're not particularly interested in frequency because the problem doesn't ask for it in this case, although we could get it just as simply as we can get the wavelength, probably a little bit more simply than what we get with the wavelength. And so I've put Planck's constant and the speed of light here, just so that we have those numbers out on the table so that we can use them. I suspect those are numbers that as you use them more and more, you'll learn to memorize, or they'll get stuck in your head. So we said the energy of the photon is equal to Planck's constant times the speed of light over the wavelength. And we know the energy of this photon is 1.937 times 10 to the minus 18 joules. That's equal to Planck's constant, 6.626 times 10 to the minus 34 joule seconds, times the speed of light, 3.00 times 10 to the 8th meters per second, over the wavelength. It is very much a plug and chug type problem. All right, we have the numbers. We have one variable that we want to calculate, and so then we can plug everything in and calculate what that might be. So I'm not going to do that all those steps right here in front of you on the board because it's something that hopefully by now you're able to do. If you have trouble with that, please come talk to me about it and we can work through it together if you get stuck on it. But when you do this, you should find that you end up with 1.03 times 10 to the minus 7 meters for that wavelength. Now, a lot of times when we're talking about photons, and wavelength of photons, wavelength of light, we a lot of times want nanometers, so even though it's not asked for here, I'm going to go ahead and convert it to nanometers, so give us some frame of reference. And I know that in 1 meter, there are 10 to the 9th nanometers. So I get a unit that's easy for us to compare, and I end up with a wavelength of 103 nanometers. Corresponds to a photon in the deep ultraviolet, so that's a fairly energetic photon. Have to be energetic to cause that transition from n equals 1 to n equals 3. That is how we would complete this problem. We calculated in the previous one how to figure out how much energy between two different energy levels. Now we figured out then how to go from the energy of the photon to the wavelength, and that's 103 nanometers in this case. If we wanted to know what the frequency was, we could have easily gone and used the energy of the photon equals Planck's constant times the frequency, or nu. We could have used that part of the expression instead of the part for the wavelength, but we didn't need that in this particular problem, and so we just calculated the wavelength. That should exhaustively cover the electronic transitions, and so now you should be able to practice those on your own.